Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last few lectures, we have been discussing an important topic, particularly that of transition metal carbene complexes, their properties, their synthesis and their structural characterization. In this context, we have learned that there are two classes of this type of transition metal carbene complexes. They are mainly called the Fischer carbene as well as Schrock carbene. We have also looked into various synthetic strategies that have been employed in preparing these two carbene complexes, mainly the Fischer carbene as well as the Schrock carbenes. And Schrock carbene. We have looked into their preparations. We have also looked into the metal carbene reaction, the bonding in these complexes. With regard to bonding, we mean the interaction of the carbonic moiety with that of the transition metal, and how these leads to different kind of reactivity for these two types of carbene complexes. We have also looked into structural characterization or characterization of these complexes, and this we had discussed particularly with respect to X-ray single crystal diffraction studies. Studies of this kind of complexes. So, this had been the sort of the topic that we had discussed in our previous lecture, and in this today's lecture we are going to elaborate these characterization methods as well as reactivity of transition metal carbene complexes. In continuation with our previous discussion on structural characterization of an Fischer carbene complex whose structural parameters were discussed in the previous lecture, we are going to now take up one example of structurally characterized example of a Schrock carbene complex and see how they compare with that of the earlier discussed Fischer carbene complexes in terms of their structural integrity and other parameters. So, with this let us take a look at a structurally characterized Schrock carbene complex, particularly that of transition metal BCP CH2 CH3 and the structure of this molecule is tantalum bound to 2 cyclopentadienyl ligand with methyl moiety and carbonic moiety. So, this compound contains a tantalum carbon single bond as well as a tantalum carbon double bond, and as a result and that is obvious from the bond distances. This tantalum methyl bond is much longer at 224 picometer, whereas because of its multiple bonding nature this tantalum carbene bond is way shorter at 203 picometer, and the angle over here is the angle between the 2 Cp and the tantalum is 138 degrees, whereas between the two tantalum carbon bonds this is about 95 degrees. So, obviously, it can be seen that X-ray is extremely good technique for differentiating the bond that exists between tantalum and the carbon of a methyl moiety, as well as that of a tantalum and a carbene of a carbonic moiety, and it shows that because of the multiply bonded nature, tantalum carbene bond is significantly shorter than that of the tantalum methyl single bond, and that can be easily distinguished by using X-ray diffraction technique. Now, we are going to look at some of the general characterizations thing that can be obtained through structural characterization, and what one sees that this geometry about the carbon center is trigonal planar, at the C carbene is trigonal planar, which means that the metal and the carbene and the two substituents on the carbon, they all lie in a same plane. They all lie in a same plane in a displaying a trigonal planar geometry. Also, from the metrical data, what one establishes is that the hybridization of carbon is approximately sp2, carbene hybridization is sp2 type. So, that means that this carbonic center is sp2 and these bond angles are somewhat about 120 degrees. Now, in our earlier example of a Fischer carbene complex, what we saw that these metal carbon alkyl substituents, these bonds have expanded from 120 degrees to somewhat 128 or 130 degrees, and as a result this alkyl carbon alkyl bond has contracted from the ideal value of 120 to about 110 degrees. So, what we see that this being a sp2 center ideally should be 120 degrees, but in specific examples they may open up from the more ideal value of 120 to about 130 degrees, whereas the alkyl CR angle in turn may sort of become smaller. The metal as observed in our earlier example, Strock carbene example, where there was simultaneous presence of a metal carbon single bond as well as metal carbene bond, multiple bond, and what we saw that metal carbene MC carbene bond is significantly shorter than metal carbon single bond, and that is significantly shorter. So, that is something that we had seen, and that arises because of metal carbene bond being multiple bonded in nature as owing to the presence of carbon to metals sigma bond as well as metal to carbon back bonding in nature. Also, in our last example we had seen that with respect to carbon monoxide, metal C carbene bond is longer than metal CO bond, carbonyl bond. Metal carbonyl bond as a result of greater metal d pi to C p pi interaction in carbonyl complex. So, what we saw that owing to greater pi acidic nature of the CO ligand is more pi acidic. What we saw that owing to greater pi acidic nature of the CO ligand, that the metal back donates more to the empty pi star orbital of CO. As a result, this metal carbon bond metal carbon bond of metal carbonyl compounds are way shorter than that of the metal carbene bond, because here the back donation is not as acute as that in metal carbonyl complex. Also, for a Fischer carbene, what was seen from the structural characterization data is that the CX bond, where X is an heteroatom, is shorter than a single bond, and this was because of C p pi to x p pi to C p pi interaction. And what we see that the carbene center is stabilized by the metal orbital, and this can be explained by in this diagram, where we have, let us say, a heteroatom attached to a carbene, and the heteroatom is in has a the lone pair, and then there is this empty orbital on the carbene, and that can interact this empty this is empty, and this is the lone pair pair. So, filled, and this is filled. So, this empty orbital can be stabilized by electron donation from the metal as well as from the heteroatom lone pair. As a result, this CX bond, as a result the CX bond because of this interaction is shorter than CX single bond. CX bond in carbene is shorter because of this stabilization or conjugation of its lone pair onto the vacant PZ orbital of the carbene center, resulting in multiple bonding character between the CX bond. As a result, it becomes shorter than that of a single bond distance, and this is mainly observed in case of Fischer carbene complexes. So, overall what comes out that a lot of information can be obtained from structural data using single crystal X-ray diffraction studies, particularly looking at various bond lengths and bond distances of the metal with the carbon or the heteroatom with that of the carbon, and that gives one the extent of relative interaction that is prevalent in each of these moieties. So, this X-ray thus is a very good parameter for obtaining an understanding of the interaction prevalent in these classes of compounds. So, now we will see that other than X-ray, for example, other spectroscopic technique like IR, Raman is also useful in understanding these metal carbene interaction, and particularly this is prominent in carbonyl complexes, which shows a lot of variation in metal carbonyl stretching frequencies, CO stretching frequencies as a result of back donation from the metal. And I am going to illustrate this with an example showing the change in CO stretching frequencies as a result of back donation from the metal center to the CO, and how that can provide input onto the electronic nature of these carbene complexes. So, for example, very useful data can be obtained using IR or Raman spectroscopy. For example, for chromium hexacarbonyl nu CO stretching frequency, this being a symmetrical molecule, one can only observe in Raman, which is 2108 centimeter inverse, whereas for the nu CO trans to carbene appear at 1953 centimeter inverse, suggesting that there is more electron donation from chromium to carbonyl in this compound than in this, suggesting more chromium to carbonyl back donation occurring in CrC OMe CH3 than in CrCO6. So, that shows that carbene is a very weakly pi acidic and strongly a sigma donating ligand, implies bene is strong sigma donor and weak pi acceptor. And when one moves from Fischer carbene to n heterocyclic carbene complexes of the structure CO5 Cr having 2 nitrogen and methyl, then nu CO trans to carbene. These carbenes are called NHC. This is called NHC. So, new trans to carbene appears even down at lower energy at 27 centimeter inverse. This implies that NHC is a very strong sigma donor ligand and with extremely poor pi accepting nature. So, what it shows that how the metal carbonyl metal carbonyl frequencies shift as a result of this metal to carbonyl back donation that appear in complexes where their carbene is a ligand along co-ligand along with metal carbonyls. For example, in this chromium Fischer carbene carbonyl complex, the carbonyl trans to chromium show a stretching frequency at a much lower energy as a result of strong chromium to carbonyl interaction, which arises because of electron donating nature of the carbene moiety. Now, as one goes from Fischer carbene on to N heterocyclic carbene, which is even more electron donating as compared to the Fischer carbene, as a result the metal carbonyl interaction gets even more stronger, resulting in much lower nu CO stretching frequency at around 1927 centimeter inverse. So, these mixed carbonyl carbene complexes provide a good handle at looking at the extent of electron donation that occur between carbene and the metal center, and as well as the co-ligand carbon monoxide, and provides a useful tool for quantification of electron richness of this carbene by looking at a series of this kind of complexes. A good illustration of such electron donation occurred in metal carbonyl complexes having co-ligands as carbenes is shown in the example discussed here. Now, thus IR provides a very good example of how this can be used to gain insight into the pi acceptor and sigma donating nature of these ligands. Okay. Apart from IR, carbon NMR is also a very useful method where one can look at the chemical shift and then try to guess at the type of reactivity that they can show. And what is obvious from here that this metal carbene resonance spread over huge range, and that one cannot obviously sort of distinguish their reactivity by just by looking at their chemical shift. Okay. So, 13C NMR, in 13C NMR the C carbene resonance spread over a wide range, and for example, one can sort of see that for Cp2 methyl tantalum CH2 13C NMR del ppm, this is arrives at 224, whereas for another Strock type compound T butyl CH2 whole 3 tantalum C T butyl hydrogen, this comes at 250, and then CO5 chromium carbene hydrogen in Me2, this is the Fischer carbene, this has 246 ppm, chromium 5, CO5 chromium C pH OMe, this comes at 351 ppm, CO5 chromium C pH 399 ppm, and one when one looks at the reactivity, reacts as there is no correlation as to kind of reactivity that is disclosed. For example, display. For example, this Schrock carbene having a chemical shift of 224 ppm in carbon reacts as a nucleophile, whereas the tantalum one, which also has somewhere very close chemical shift of about 250, reacts as a nucleophile, whereas this Fischer carbene, which is also exactly of similar chemical shift, behaves completely different and reacts as an electrophile. And this another Fischer type carbene showing at appearing at very high carbonic resonance of 351 also behaves like an electrophile to that of chromium carbonyl appearing 399 also react as a electrophile. So, what we see, one can conclude that the carbonic moiety appear in a wide range from 220 to about 400 ppm, and they can appear in any of this range, and it is very difficult to predict the reactivity just based on the chemical shift carbon resonance, because we can have Fischer carbene or Schrock carbene showing almost near equal chemical shift, but showing extremely opposite reactivity. So, this is consistent with the fact that the carbon resonance indeed vary a lot. For example, for the tridyl cation CH3 plus, that this del is 212 ppm, and for methyl Me3 plus this is 336 ppm. So, even for this cation on going from the methyl to phenyl substituents, there is a huge the difference in chemical shift. So, from the carbon characterization, one can say that even though the carbene moiety has been characterized, but any attempt to draw correlation based on their chemical shifts on the reactivity of these complexes may not be useful, because there may be carbene complexes which has comparable chemical shift, but probably a equally opposite kind of reactivity, as can be seen from this Schrock and the Fischer carbene complexes which behave totally different, live to each other. So, with this, let me conclude today's discussion. We have looked at various characterization or methods that are often used for characterizing metal carbene complexes. In this regard, we started the lecture by looking at structural characterization of Schrock carbene complex, and looked at how the metrical data can indicate towards the kind of interaction that is prevalent between the carbonic moiety and the metal center. Having looked into that, we have also looked at other forms of characterization which provides insights into the metal carbene interaction, and that included IR Raman spectroscopy, where we saw that how heteroelectric complexes of transition metal carbonic moiety and carbonyls can be used to quantify the extent of electron donation the carbene offer onto the metal center by looking at the metal carbonyl stretching frequencies, and how that can be made a useful tool for analyzing the electron richness of the carbene ligands that are bound to the metal center. From the examples that we have discussed, we have also seen that carbenes are predominantly sigma donor with very little pi acceptance ability, and that when a carbonic moiety is attached to a metal carbonyl complexes, the metal becomes more electron rich, and as a result the metal carbonyl bond trans to the carbene moiety shows CO stretching at a much lower energy arising because of the more metal to metal carbonyl back donation interaction. We have also discussed about carbon C13 characterization of carbonic moiety, and what we have seen that this carbonic resonance of can appear in a widespread range of chemical shift, and that it is not useful for characterizing their reactivity directly with their carbon 13 NMR resonance. So, with that let me conclude today's lecture. We are going to be discussing carbene a bit more details, as these are very important molecules having lot of applications in chemical catalysis, and also has been recognized by the Nobel award in 2010 for olefin metathesis. So, a lot more of carbene and more insightful discussion in the next lecture in terms of their propertivity and reactivity that we will look up. That is going to come up in the next lecture. With that, I thank you for being with me, and I look forward to being with you in next lecture. Goodbye.